Alrighty, today we are doing 5.1b if you're a member of one of my classes. If not, we are actually covering verifying trigonometric identities. This is part 2. We had an intro lesson yesterday. That was 5.1a. Today, the skills we're going to be practicing with these trigonometric identities are factoring by difference of squares. So yesterday we factored the GCF. Just to remind you, yesterday we went over this as well, but when we're factoring, if you look at the tricks to try that we looked at tangent squared x minus cotangent squared x. Because these were perfect squares, we could factor them using the difference of squares, much like if I had x squared minus 4, then that would factor to the pattern x plus 2, x minus 2. So we're practicing that skill today. The other skill we're going to be practicing is using those even and odd identities. So everyone should go ahead and get out their identity sheets. They are nicely colored with this salmon colored if you're in my class. If not, you probably have something similar. So these are the ones we're going to be using today. So in yesterday's lesson, we used Pythagorean identities, quotient identities, and reciprocal identities. And in today's lesson, we're using those even and odd identities. And what these say is that if you have the sine of a negative angle or the tangent of a negative angle, then those are odd functions, meaning that they will have opposite signs for their opposite angles. However, if you look at good old cosine, which is right here, cosine actually has an even behavior, which means when you plug in negative x values, it reflects it across the y-axis, so your output is exactly the same as when you plug in positive x. So these ones would be reflected over the x-axis and you would have negative outputs. This one you have a positive output. That's a little tricky. This all stems from something like this, so I'll go over this briefly. If I take a look at the sine of pi over 4 and then compare it to the sine of negative pi over 4, pi over 4 would be root 2 over 2 because that corresponds to a special triangle angle of 45 degrees. And then if I look at negative pi over 4, what this says is if you have the same angle but it has an opposite sign, you'll get the opposite of what you got when you plugged in a positive angle. So the sine of pi over 4 is positive root 2 over 2. However, when I graph negative pi over 4, which is down here, I get the opposite of that, which is exactly what this identity is saying. You will get the opposite as if you plugged in the positive angle. However, good old cosine of pi over 4 versus cosine of negative pi over 4, look what happens with cosine. With cosine, we actually look at the x value because its ratio is x over r. So with cosine of pi over 4, we look here, and cosine of pi over 4 is root 2 over 2. When we take a look at the cosine of negative pi over 4, we're still looking right here because it's a 45-degree angle, and in the positive x direction, it's still positive root 2 over 2. So what this is saying is, if your sign is positive or negative, you're still going to get a positive or the same sign as cosine of just the positive angle. So again, if I have cosine pi over 4, I get positive root 2 over 2. And if I were to take a look at cosine of negative pi over 4, this is saying I would not change the sign as cosine pi over 4. So that's pretty cool. We still get root 2 over 2. It works out with our unit circle. A little tricky, but that's the one that you're going to want to watch out for is good old cosine. Of course, the reciprocals follow suit. Okay, the other skill we'll be practicing in this section is to use a variation of the Pythagorean identity. So we are used to our Pythagorean identity looking like this right here. Sine squared x plus cosine x squared x equals 1. And it's going to look very similar, but I just want you to be familiar with a variation of it. So I think with all that, we're ready to begin our part 2 of verifying trig identities. So I'm going to go ahead and zoom in just a little bit more to make it easier for you to see. So let's go ahead and take a look at example 1. So it says verify the trig identity. So what you can see over here is that the numerator is squared. Remember, we talked about having to look and see where you're going. Over here it's not squared, so that's going to clue me in to maybe approach this a little differently. Now this side is one fraction, and we practiced the skill of splitting into two fractions yesterday, but we can't use that approach here because this has two terms in the denominator, and you can only split fractions when you have one term in the denominator because it will have meant you've gotten a common denominator already. So just be aware of that. So what I'm going to do instead is I'm going to use the difference of squares right here. So that would be tangent x plus cotangent x times tangent x minus cotangent x. And you can see you guys are given problems mostly, I mean pretty much everything that you can actually verify. Like there is some way to go from the left side to the right side mathematically. So that's nice. There's no trying to trick you with this here. So these problems are what we call rigged. So they are meant to work out. So you can see right away what happens. These are both factors, and this factor can cancel. And in one nice step, we have verified the identity. So we're just going to finish it off here properly by writing proper notation with identities, which is to write both steps throughout. And if you need to, you might just want to write up here that the skill that you're practicing is factoring by difference of squares. And if that is something that you need a little bit of review on, you can Google it. But what I also will point out is if you had a squared minus b squared, the pattern for difference of squares is that you have a plus b times a minus b. These are called conjugates of each other right here. And the nice thing about conjugates is whenever you multiply them together, your middle term cancels out. So that's pretty cool. Give this one a check mark and let's move on. Okay, so on this one, before we even get started, we're going to take a look at the problem. We see that there's this negative x and it's with cosecant. So we're going to want to take care of that first. So in this particular problem, we are practicing our even and odd identities. So we're actually only going to practice one, but we have that little sheet there. Now remember, cosecant's reciprocal is sine, so it's going to follow the same procedure as sine would. We talked about when you plug in a negative angle into sine, you get the opposite output as if you would have plugged in a positive angle into sine. The same thing happens for cosecant because they are trigonometric pairs. So what we're going to do here, very first step, is we are going to start by evaluating this. So what's going to happen is because this is cosecant and not cosine or secant, we are going to change this sign and make it a negative out in front. So again, the reason why we're doing that is because this rule right here says that if we do cosecant of negative x, another way to write it is where the angle is actually positive, but you bring the negative out in front. So that's what we have right here. That's that step that we've kind of put in here. So now we have secant x minus cosecant x all over secant x cosecant x. And we're going to be consistent and write sine x minus cosine x. So here we are at this step right here, and we're like, okay, well, what do we do now? So yesterday or the previous lesson, we went and we had tricks to try. So it's a good idea to have this lesson out. So the first one of the tricks we learned was to put it in terms of sine and cosine. We could learn to get common denominators, which really doesn't apply to this situation because if we get common denominators, what you notice it already has a common denominator. So maybe you want to split into sines and cosines first, but looking ahead, just doing like a quick little bit of math mentally, what I'm noticing is if I were to split this into two fractions, this way and this way, then what would happen is the secants would cancel out in one piece of the fraction and the cosecants would cancel out in the other part of the fraction. So I'm going to try that approach, and then after we're done with this problem, I'll show you if your brain told you to go to converting to sines and cosines, what it would look like. So this one is secant x all over secant x cosecant x. This is how we split into two fractions properly. Both of the numerators, both terms in the numerator, get the common denominator. So here we are. Then the secant x are going to cancel, but I get 1 over cosecant x. And here the cosecants are going to cancel, and I'm going to get 1 over secant x. And what's nice about this is 1 over cosecant x is sine x. And 1 over secant x is cosine x. So that's what I get right there. And I have verified the identity. Now I know back in this step right here, after you've simplified the even and or odd identity, in this case it's an odd identity, what you are going to maybe try, because we did it so much yesterday, is you might want to try putting in terms of sine and cosine, because you're not as comfortable as you are with splitting splitting into two fractions as you are with sine and cosine. So what we're going to do is take a look at what would happen if you did it that way. So if you were to do it that way, then you would have 1 over the cosine of x minus 1 over the sine of x, and then I'm switching the denominators here as well. So notice this says alternate way. Clearly this might get you there a little bit faster, but it's the journey, not the destination. So if your brain told you to go here, then that's great. So I get 1 over cosine x. Right here, minus 1 over sine of x all over 1 over cosine x minus sine x. Sorry, times sine x. So we have sine x minus cosine x over cosine x times sine x. So how did I go from this step to this step? I got common denominators. And then what we're going to do from this step to this step is copy dot flip. So you copy your numerator, then you're going to change your division bar to multiplication and flip. And if you notice when you do that, those cancel out, and what do you have? You have the identity verified. So if that was what your brain was initially telling you, it still will work out for you. This is just another tool to add to your toolbox so that maybe you can approach these differently. Okay, so moving on, we are going to now take a look at that variation of splitting it. So variation of the Pythagorean identity sine squared x plus cosine squared x equals 1. And actually, what I want you to recognize is that whatever is next to the trigonometric function here, sine or cosine, is representing an angle. So I am going to change this from x to theta just to give us that reminder. So as long as I have sine squared of some angle plus cosine squared of some angle, I can write it as 1. So you might be thinking, how does that apply to this problem right here? Well, the way it applies is you're looking at this and you're kind of like, wait, I see cosine squared and I see sine squared, but right here it says 2x. Remember that this is just representing the angle. So x is the variable. I'll tell you the variable is like 45 degrees. Before you can evaluate the trig function of cosine squared, you would just have to double it. So 45 times 2 is 90. But you'd be doing the same thing over here. So really, you're still doing cosine squared of some angle plus sine squared of the exact same angle, which means that we can take this whole thing here and make it 1. So this would be cotangent squared 2x plus 1 equals cosecant squared 2x. So again, this Pythagorean identity is so awesome and so versatile. It's saying sine squared of some angle plus cosine squared of the exact same angle if you have that pattern it equals 1. Don't get hung up on this being 2x instead of just theta or just x. It's still representing an angle. The difference is that before you can evaluate, I'd have to multiply whatever number I had by 2, but since I'm doing the exact same thing here, it's still 1. Okay, so then you're like, okay, maybe I want to switch this to sines and cosines. But before we do that, we're remembering because it's squared, it's always a good idea to look at our Pythagorean identities. So this side involves cosine squared 2x, or sorry, cotangent squared 2x. So we go over here, and what do I notice? I notice that on this paper, if I have 1 plus cotangent squared x, that's the same thing as cosecant squared x. So this angle is x, and over here this angle is x. I have the exact same pattern. Look at this. Cosine squared of 2x and then plus 1 is equal to cosecant squared of 2x, which means that I get to rewrite this using the identity sheet. So all of this piece right here is a Pythagorean identity, and it becomes cosecant squared 2x. That's pretty nifty. So now we're plugging right along. We're going to go ahead and move up to example 4. What I'm going to show you with this trick right here, which I didn't write down on the paper, but still worth noting, is sometimes we work both sides. So far in 5.1a video and in this video, I've only worked one side, and we generally pick the left side because it's generally more the complicated side. Do you have to stick with that? No. Is it common math practice? Typically. So with this problem right here, I'm going to approach it as if I didn't know I was going to work both sides. So the first thing that I would do was, because I have two fractions and they're already in terms of sign, I would go down my list of tricks to try and see that I should probably get common denominators. So I'm going to give this one a 1 plus sine theta and a 1 plus sine theta. And this one needs a 1 minus sine theta. Now if you look, that's pretty cool. Like, talk about rigged, because what did you just create here? So in the problem just to the left of it, we started with perfect squares and we factored it into the difference of squares pattern. But over here, we're going to be given this a plus b, a minus b pattern, and know we can multiply it together to get that pattern as well. So in the numerator, I'm going to end up with 1 minus sine theta, because 1 minus sine theta times 1 is 1 minus sine theta, plus 1 times 1 plus sine theta. And in the denominator of this side, I am going to make sure to multiply these together, and I'm going to use the difference of squares pattern, so this would be 1 minus sine squared theta. And that equals 2 plus 2 tangent squared theta. So before I continue, just one idea that popped into my mind as I was working this was, you could pause the video and try this and see what you would do and see where you get stuck, and then come back to the video and see what I did. Or maybe you're able to complete it without watching the video, and that just shows your skill level and that you're progressing with these. Don't worry if you can't do it without watching the video. This is not something that's totally like the easiest thing in the world to do, but it's a good idea to kind of test yourself. So just saying, maybe stretch your brain a little bit and try that. I know we always like to see the teacher do it, but where we really learn is from when we try it ourselves, and maybe we fail at first, but failure leads to success. So you fail at first, so you watch the video, you pick up from it, your brain holds on to it better because it's already tried it. And then the next time you see something similar, your brain will know it because it's already made the mistake one time and it doesn't want to make it again. So brains are awesome. Anywho, these are going to cancel out right here because they're opposite signs. And so I'm going to have 2 over 1 minus sine squared theta. And you might be thinking like, okay, cool. Well, Wolken said the Woken way is, if you see squares, to go ahead and look at the Pythagorean identity. Some of you probably already have this memorized. Some of you don't. You're getting there. I know it. So what I noticed here is another way to write 1 minus sine squared of some angle is cosine squared of the angle. So I'm going to change this right here to 2 over cosine squared theta. Now that's pretty simplified. Some people might want to keep going, so let's try it, because why not? So this is still 2 tangent squared theta, and in the spirit of trying to work one side, I'm going to keep going. And the only other way to change this is to write this, 2 over 1 over cosine squared theta, which is secant squared. So the very simplest way for me to write this is like this. So you actually can do this problem without working both sides, but let's say our skill level, we're just not comfortable. We don't really see where to go with the left side. We feel like it's as simplified as we can go. So if that's you, totally okay to go to the right side. So instead of repeating the right side throughout the problem, I'm going to switch over and go to the left and say, well, maybe I can simplify this a little bit. So what I can do is, I notice that it has 2's in common. Both terms contain a factor of 2, so they're both divisible by 2. So I'm like, okay, cool. Now what am I going to do? You can kind of start to see, wow, I have the 2 there. If only there was a way to change 1 plus tangent squared theta. You go, aha, I'm going to use my identity sheet. So I'm going to go to my identity sheet, 1 plus tangent squared. What's another way to write it? So 1 plus tangent squared of an angle is secant squared of the angle. So this right here becomes 2, and all of this right here is secant squared theta. Be careful when you're going back and forth between your formula sheet and your paper. Whatever angle you start with, you need to be consistent. Sometimes that's annoying for you, but I mean, it shouldn't be something that's hanging you up. After you finish a problem, real quick check to make sure your variable is all the same. Chickadee check that one off. Moving on. Okay, example 5. Oh no, I have 2 thetas in here, and this simplifies to cosecant 2 theta. Normally, this one would be a group challenge in my class because I want you to see if you can pick up what we're putting down so far in this lesson, but this is a video, so that's not really realistic. But if you'd like to pause it and work on it and then check and see, that would be a great idea. So this one right here, because this says cosecant 2 theta, I'm going to go ahead and try my first trick to try, which to switch everything to sines and cosines. So I have sine 2 theta over cosine 2 theta plus cosine 2 theta over sine 2 theta all over 1 over cosine 2 theta. So that looks like the left side was pretty complicated. I may have made it a little more complicated, but these are tricks to try, so I'm okay with it. So what am I going to do now? Next trick, maybe try and get common denominators. Like, you can look ahead and almost see where this problem is going. It's actually like so cool how this works out. I get way too excited about these things because I think it's so fascinating, and I want to share that with you, even though some of you just don't have the same interest. But like, appreciate the coolness of this, maybe just a little, just for me. So this right here is going to be sine 2 theta times sine 2 theta. And then notice what's created right here. That's sine squared 2 theta. And then here, this one needs a cosine 2 theta and a cosine 2 theta. Do you see where this is going? Now I have cosine squared 2 theta. So let's take this and see where it goes. So we have sine squared 2 theta. So that's weird. We haven't written like that. I don't think that maybe one other time, but sine squared 2 theta plus cosine squared 2 theta all over this common denominator of cosine 2 theta sine 2 theta. And whenever we have more than one fraction bar, we copy dot flip. So rather than making that another step, let's just do it right here. We're going to copy dot flip this cosine 2 theta over 1, and then copying the right side, which is standard protocol. You will get marked down on tests if you don't do that if you're in my class. So cosine 2 theta is going to reduce, and then this right here is going to equal 1. So sine squared 2 theta plus cosine squared 2 theta. It's the Pythagorean identity. Is it exactly what we have in our sheet? No, but we're okay because we know that as long as we have the same angle and we have the same signs for sine squared and cosine squared, then we can use the identity. So now we're at 1 over sine 2 theta. Over here, this is just 1 over 1, so that's just 1, and 1 times anything is itself. So here we are, and 1 over sine 2 theta is cosecant 2 theta. So cosecant 2 theta equals cosecant 2 theta, and that's where we're at. I do want to show you an alternate way, and I'm just not going to take the time to write this out because that would just take a lot of time. So I've already written it out just so that you can see. So let's take a look at this one right here. Alternate way, it's going to go over here a little bit, but let's just follow. So here's our starting problem, tangent 2 theta plus cotangent 2 theta over secant 2 theta. A student reasonably may go to something like this. Well, there's one fraction here, so their brain might say, hey, in example 2, when we only had one fraction, we split it into 2, so maybe we should try that. So if you split that into 2, this is what you would get right here. And then you might go, okay, split it into 2 fractions, so now I need to switch to sines and cosines because nothing reduced. Now I want to pause and just say something because you can save yourself a little bit of work here. On the left side, how many, this is something you can split into 2 fractions. How many terms are on the right side? There's only 1. So splitting it into 2 means at some point you're going to have to come back to 1 because the right side is in 1. Versus when you look over here, when you have secant x, this right here, look at your right side here. How many terms do you have here? You have 2. So splitting it into 2 fractions will be more beneficial because you're already splitting it up into the 2 terms that the right side has. So over here it only has one side, so that initial approach is probably the quicker approach, but again, journey not destination. So let's keep going with this right here. We switched everything to sines and cosines, and now we have to copy dot flip this fraction, and we have to copy dot that fraction. So you can see my arrow coming over here to do that. This one cancels. So I have sine 2 theta, which is from the first fraction, plus cosine squared 2 theta over sine 2 theta. Now I have 2 fractions, but again, I'm going back to 1 on the right side, so I went ahead and got common denominators. So this one would be a sine 2 theta, and this one would be a sine 2 theta. So I get sine squared 2 theta plus cosine squared 2 theta, which is 1 over the sine of 2 theta. So back to where we started, which is great, but a different approach, one that works. Alrighty, so let's finish up these last 2 examples on the back side that we will be working to help us. So on a problem like this, there's many different approaches that you can take. Some students look at this side right here and think it looks a little more complicated, so they might choose to multiply by the conjugate. I actually value that approach because this ends up being squared because of that 2 right there. So multiplying by the conjugate introduces the square to the right side, which is a great strategy. Like that's a good thought process to have. However, on this particular problem, I'm not going to do that because I'm going to follow what I think a typical person might try. So I think what somebody might try in this problem is to actually switch these to sines and cosines. So that's that right there. And what this means now is, oh look, there's 2 fractions. They have a common denominator already. Woohoo, because then I don't have to get a common denominator. So I'm just going to write this as a single fraction. So in the numerator, I have 1 minus cosine x. In the denominator, I have the sine of x, but they are both squared because of the square that's right up there. So if you're looking at this, you're like, I'm getting a little bit closer here. How do I know I'm getting a little bit closer? Look at that numerator and look at that numerator. Difference, this numerator is squared, but we're a little bit closer. So again, we notice that this numerator is squared as well as the denominator, because that 2 means repeated multiplication in both the numerator and the denominator. So in the numerator I have this, and in the denominator I have this. So you might be going, okay, great, now I have part of the numerator, but this denominator over here says 1 plus cosine x. This denominator says sine squared x. Over here, it's in terms of cosine. If only there was a way to switch our sine squareds into cosine squareds, that might be helpful. Oh wait, there is a way. So this only works if it's squared though. We're going to go back to that Pythagorean identity, and right there, we wrote in a variation of sine squared x plus cosine squared x equals 1 is if you solve it for sine squared x, and you would get 1 minus cosine squared x. So we're like, oh cool, that's getting me even closer. So the numerator is staying the same, but I am changing the denominator to 1 minus cosine squared x. And what you are probably noticing is 1 minus cosine squared x is actually now a difference of squares. So if we have that difference of squares, what we're going to do is factor it. So numerator in this step is again staying the same. And then the denominator, this is a difference of squares. So it's going to be 1 plus cosine x and 1 minus cosine x. So we are super happy with that manipulation. I call it a manipulation because you changed it to the form that you could use. Like, we manipulate in math all the time. We change things or reverse the order. Instead of multiplying, we factor so that we can use it to our advantage so we can complete the task that's assigned. So this term and this term canceled, and if you look right there, we're going to make our final concluding statement. We have 1 minus cosine x all over 1 plus cosine x equals 1 minus cosine x all over 1 plus cosine x, and give it a check. So there's that one. The last one for today isn't actually asking you to verify. So you don't have to write this the whole way down. So you're going to see me take a different approach. The only difference is that in this one, because it says verify and there's an equal sign involved up here, I'm writing the right side through every single step. There's no equal sign here. Expressions don't have equal signs, equations do. And so I just need to show that I can get this to cosecant theta. So I'm going to start by switching everything to sines and cosines. The reason why I'm doing this is because I'm not quite sure what to do. I'm not going to try and use a Pythagorean identity because it's squared. I don't see any factoring I can do. I can't get common denominators. I can't even split into 2 fractions because there's 2 terms in the denominator. What I know I can do is switch to sines and cosines. So this is 1 over the cosine of theta plus 1 over the sine of theta all over 1 plus sine theta cosine theta. Once I do this, I can see, now I can start talking about common denominators. So here, this one would need a sine theta, cosine theta, cosine theta. I don't have squares, but that's okay. So in the numerator of this fraction, I am going to have a common denominator of cosine theta, sine theta. In the numerator of the numerator, I'm going to have sine theta plus cosine theta. So that's coming from right up here. Moving on, now I need to get common denominators in the denominator. So I'll write this over 1 cosine theta, cosine theta. So in the denominator, I get cosine theta plus sine theta all over cosine theta. So then we learned our next step here is to copy dot flip. So we are going to get sine theta plus cosine theta all over cosine theta sine theta and multiply it by the reciprocal or the flipped fraction cosine theta all over cosine theta plus sine theta. And you might just pause for a second and see what you can reduce. So at first these don't look the same, but remember in math 1 plus 2 means the same thing as 2 plus 1. It's called the commutative property. And so this and this are in fact the same thing. So those are common quantities that can be reduced. Then the cosine theta and the cosine theta are common factors that can be reduced. So remember to keep your placeholder of 1. I have 1 over sine theta, and 1 over sine theta is cosecant theta. So just a friendly reminder that you will have to sometimes erase and start from fresh. You might have to take different approaches. Just keep working at it, and maybe you might need to take a break for a little bit. You might need to call someone and ask for help. But this is something you can do, and something that's really good for your brain. So keep working at it and have a great day.